Hi, the next algorithm that we will talk about is the Bernstein Vazirani algorithm. And the setup is the following. We have a function f, again from 0, 1 to the power n to 0, 1. And we are given that there is a secret string a. So there is a secret string a such that f of x is equal to a dot x. And our goal is to call these functions or query this function as less as times as possible to find the string a. So query f to find string a, right? So it seems that over here also you will require an exponential number of queries. So, but however, one can use a simple trick. Call the function f. So call f with x is equal to, so 1, initially you can call it with 1 in the first position and 0 everywhere else, right? So if you call f with this, then you will get f of x is equal to a dot x. And since x is zeros except in the first position, you will get f of x will be equal to a1. So this will be your first call. So you have the first bit of the secret string a. And then this will be your first call. And then the second call may be something like this, is equal to a dot x. And in this case, x will be equal to 0, 1, 0, 0, 0. So it will be 1 in the second position. And if you do that, you'll notice that you will get a2. And if you make n calls like this, you will get all the, so in n calls, you will get the secrets in. So A is obtained. So now the Bernstein Vazirani algorithm is a quantum algorithm to find the solution to this problem. And the algorithm finds the secret string in only one call to this black box or U of f function. So let's see how that works. Okay, so the nice thing about the algorithm is that the circuit for this algorithm is identical to the circuit of the Deutsch-Jozsa algorithm. So let's draw that circuit. So let me just draw the circuit for this. So it's looks identical to the okay. So these are the initial states as before. This is U of f. Then this is again H tensor n. This is the measurement. And finally, you get a classical result. So this is again the circuit, except that, of course, the U of f implementation will be different because you are implementing U of f for f is equal to, f of x is equal to a dot x. F of x is equal to a dot x. But when we are looking at the complexity of this quantum algorithms, we are trying to look at the number of queries that we make to this U of f. We are not at the moment concerned about the implementation details of U of f. Regardless, let's look at the how we can uh, analyze this circuit. So again, let's look at the various points where we're going to look at the quantum state. So this is psi 0, psi 1, psi 2, psi 3, and so on. And then let's analyze the circuit. So let's look at the initial state psi 0. This is equal to 0 tensor n tensor 0 minus 1 over square root of 2. This is the same state as the Deutsch-Jozsa algorithm. Then we have this Hadamard gate that gets applied on the first set of qubits, right? So you have psi 1 will be equal to 1 over 2 to the n over 2 summation x belongs to 0, 1 power n x tensor 0 minus 1 over square root of 2. And then you have this query function u of f that gets applied. So psi 2 will be equal to 1 over 2 to the n over 2 summation over x belong to 0, 1 power n minus 1 to the power f of x, but f of x is equal to a dot x in this case. So this will minus 1 to the power a dot x, x tensor 0 minus 1 over square root of 2. And then finally, we have another Hadamard gate that gets applied over here on the top set. So now you will have a Hadamard gate, and recall that Hadamard tensor n applied to x is 1 over 2 to the n over 2 summation z belonging to 0, 1 power n minus 1 to the x dot z, right? This was one of the propositions that we did last time. And so if I apply the Hadamard gate to psi 2, we'll get a double sum, and I can rewrite that double sum as before. So psi 3 will be equal to 1 over 2 to the n summation z belong to 0, 1 power n, and then summation x belongs to 0, 1 power n minus 1 to the a dot x plus x dot z and tensor 0 minus 1 over square root of 2. And then finally, we have to measure over here. The final step is to do a measurement on the top n qubits. So as before, in this case, let's look at the coefficient when the outer sum z, the coefficient when z is equal to a, coefficient when z is equal to a, when z is equal to a, these two will be a dot x plus a dot x, and therefore this will be a plus 1 over here. So the coefficient will be equal to 1 over 2 to the power n summation over x 1, right? Because when z is equal to a, then the inner sum will all have minus ones, and there are 2 to the power n of them. So this will be equal to 1. So the probability amplitude when z is equal to a is 1. And therefore, when you measure finally, the only answer that you can get is a, because the whole probability is concentrated at a, and therefore there is zero probability of you getting any other answer other than a. So therefore, measuring gives a with 100% probability. And therefore, you have, with only one call to this black box function, you have determined this secret string A. And notice that the circuit is exactly the same as the Deutsch-Chooser circuit. So that is the Bernstein Vazirani algorithm.